So today we're gonna talk about our first experiment, which is stress strain curve. We're gonna use a 3D printed material, some specimen to check those things. I don't know if you guys remember or not, but we talked a little bit about it last class. So basically, what we're doing over here, first we will 3D print with a specimen, then we'll put it under tensile load. We will study the deformation in the material in the specimen, and then we'll generate a stress strain curve based on that deformation. And finally, you'll see what kind of deformation or what kind of failure is happening in this specimen, and you have to make a comparison on those. So the first thing is, what is stress strain? Um, I guess at this point, you guys are very familiar with tensile force, compressive force, stress, strain. But just to give you a little bit of refresher. So when you pull a material from both its sides, and when the force it's perpendicular to the deforming surface, this is when we see tensile force in specimen. For example, let's see over here. Can you guys see my cursor moving? Yeah? No? Okay. Mm, how about now? It's a little hand. Okay. So basically, if you look at the surface and the load, the direction of them are perpendicular to each other, right? And you're pulling it up. So this is tensile force. Now, when you're stretching it, when you're pulling it outwards, that's tensile force. But when you're pushing it inwards like this, but the direction is still perpendicular, then you have compressive force. And for the shear force, when you're kind of like sliding these two surfaces, or you can say when the force is parallel to the deforming surface, this is when you see shear stress. But for our study in this experiment, we will just study tensile force. So what's the equation of it? Uh, Pretty simple. It's force over the area. Now, what area I'm talking about? The area that's the cross-sectional area that's gonna see the deformation. For example, when you are putting the force in here, the tensile force, you're considering this surface, this perpendicular surface. Now, when you're pulling the shear force, even though you might think that this is the area that you should look for, but that's not true, because the area that's gonna see the deformation is gonna be this area, because that's parallel to the force. Does it make sense? You guys have any question? Okay. So the first math, it's pretty simple. You got a cylinder of 5 inch, and then you are putting a force of 3 Newton. 3 Newton here, 3 Newton here. So find out the stress. Again, the stress equation is force over the area. So just you can apply this equation and find out the stress. I'll give you a minute to solve this. Um, Let me know whenever you're ready to share the answer. Yeah, you guys got it? Anyone? Okay. Edward got 0.153. All right, that's one answer. Anybody else? 0.1527. Okay, I see. Okay, so perhaps you guys are making a couple of mistakes. Let me show you. 0.153. I think what you guys are doing right now, it's your as your area, you're using inch as a unit, but you have to be like really, really vigilant that all your units are consistent throughout the whole process. So we're using Newton as a unit for force, and Newton is kilograms times meter per second square, right? So that's the system is in meters, but this is in inch. So you have to convert the inch into meter and then plug it in, and then you'll get the value. I think I got a couple of questions. Yes. Yeah. So you guys are familiar with the concept. That's good. Uh, so what's the force over here? The force is 3 Newton, but you have two forces, one in here, another in here. Or you can say if this thing is attached to a wall, then you can say you have a force and then you have a reaction force. But for your case, you're just pulling these forces, like pulling this cylinder with two different forces from the opposite sides. So you have total of 6 Newton, and the area is pi by 4 diameter square, and diameter is in meters. So pretty simple. Now let's do this one. So now you know that you have to do the conversion, but which area you're going to use over here? I'll give you a minute. Diego is asking, what did we need to convert? You need to convert the unit system, meaning you have the height as inch, but the force is in meters. So convert the inch into a meter and then get those areas. All right. Have you guys got any answers? Anyone? All right. Guess it's a little tough, huh? Pretty simple. So the force is pretty similar, but the area, you have to consider this little area over here. So you might think that it's the cross section of these plates, but no. All you're looking into is the cross sectional area of this little bolt over here. And the diameter of the bolt is 1 inch. So that's all pretty much you need. So you just plug this thing in, get the area of the bolt, cross-sectional area of the bolt, and then you'll get your shear stress. Even if you like use common sense, that makes sense, because when you're pulling these two parallel plates together, if you think about it, the only thing that's gonna break eventually is the bolt. The cross-sectional area of these plates is not gonna change. So uh, that explains it as well. Now comes the definition of strain. What's strain? Uh, Strain is defined as the deformation of a solid due to stress. Meaning, let's say you have a rod, you have a cylindrical rod, and you are pulling it outside, you're putting it under tensile load, what's going to happen? The material, like along this length, the rod is going to change its measurement, right? It's gonna get bigger. I wouldn't say bigger, it's gonna get longer in only in this direction. So you have an initial length and then you have a change length and then you have a change of length. So strain, it's the change of length over the initial length. Does it make sense? Yeah. Okay. I okay, I think I moved a little fast. You guys had a couple of questions. Why did you multiply the last one by 2? Okay. It's because you have two forces, not only one. The value of V is C Newton, but you have V and V. That's why. Make sense? Okay. So that was strain, and then comes a Poisson's ratio. So that this example, the example of the rod, it's an example of a uniaxially loaded rod, meaning that you're only applying load in one direction, or you're only considering the length change in one direction. But what if it's a two-dimensional object, or what if it's a brick? What's going to happen? Let's say you push a brick inside, you put it under compressive load. So definitely it's going to squeeze, right? It's going to its length along this axis is going to go down. However, you know that the total amount of mass in a material is constant, and since it's a solid, then the volume containing this mass has to be constant as well. So if the brick is changing its length along x-axis, then where the masses are going to go? That explains the Poisson's ratio. So when any material, any specimen changes along a load, so if the the dimension, if it gets shorter in one side, it has to get longer in other side. So Poisson's ratio is the ratio of two different axes, the change of length in two different axes. For example, over here, you have a change in length along x-axis, which is getting smaller, right? And then you have another change in length along y-axis, which makes it getting elongated. So you divide them, you get the Poisson's ratio. But there is a sign, the negative sign. Why is it in here? It's because definitely if you squeeze it in one direction, then it has to get expanded in other direction. That's the only way to go. Like you cannot squeeze it from all the direction, meaning you're not keeping the volume constant. You're making it either like you're changing it. So without changing the density, it's not possible. So it makes sense that these changes in length, they has to be in a different magnitude, in opposite magnitude when they're deforming. That's why there always is a negative sign in front of the Poisson's ratio. So if your sigma x, I'm sorry, your eta x is positive, then your eta y will be negative. So this negative and this one will cancel each other, and you will have a positive like numerical value. The other way is true as well. Let's say you're pulling it apart, so your x is going to be positive and your y is going to be negative. If you're putting it under tensile load, you're along the x-axis, it's gonna get some more length, and along the y-axis, it's gonna lose some length. So eventually, you're gonna get a positive value. Make sense? Any question? Okay. If not, then let's do this problem. This little math over here. You have a steel beam supporting a bridge approximately 100 meters tall. The change in length is 0.01 meters. if the steel beam expands approximately this meters in the transverse direction and original width is 0.1 meter, what's the Poisson's ratio? Um, you can solve it by yourself before looking at the solution. Then I'll go by the steps. But I'll give you guys 2 minutes to see if you can solve it by yourself. Okay. So you have the initial length of the bridge over here, and then the change in length in two directions, in transverse direction and in the longitudinal direction. Longitudinal it's zero point zero 0.01, but since from the picture you can see that it's a compressive force, so definitely along longitudinal it's gonna lose some strength, lose some length. So you use this equation, but and you use this negative sign. And along transverse you have the opposite change. So you put it in here, you got the second thing. You divide them over and you get the Poisson's ratio. Any question? Okay. So I'm pretty sure you guys have seen this curve several times along your studies in here. So what is a stress strain curve? The one that you guys are seeing over here, it's a ductile material curve, meaning it it changes its properties along different stress range. For example, if you think of a rubber, like a like an eraser, like a big eraser. So you put it under stress and it deforms, it deforms, it deforms. But up to a point, if you let the strain go, no matter however deformed it was, it eventually is going to go back to its uh, initial length, right? But if you still keep putting it under pressure, if you still keep pulling it apart, eventually at one point, even if you let it go, it would still have, it can reach back to its initial shape. This is this point. We call it the the plastic deformation point. I'm looking at this point little right here before the yield point. So even if you let it go at this point, what you're gonna see, like this thing is, its shape is gonna go down, but eventually it's gonna stop over here. So initially its starting point was here, now it's here, meaning that there's a permanent deformation in here. That permanent deformation is, you can call it like a permanent strain in here. After that, if you still put it under stress, at one point you're going to see that its shape, it's going to decrease, it's decreasing. That's kind of strange because um, you think that as you put it under stress, its area or its volume is going to go up and up, but that's not going to happen. But why not? We'll explain it in a bit, and that's an important phenomena in this experiment. And from there, if you still keep it under stress, it's going to go up, and ultimately at one point, the bonds are the you can see that after this point, increasing stress has no effect on the shape whatsoever. So what's happening at this point? At this point, the specimen is pretty much broken all the way. Like it lost its molecular adherence, so it doesn't have the material properties that you would expect it to have. And finally, at this point, it just breaks. So but that's the fracture point. So what's the modulus of elasticity? Explains with this equation, where you have the stress equals to E multiplied with strain. It looks familiar. It looks like Y equal to mx. And what's Y equal to mx? It's a we call it I forgot the term. It's called the straight line that goes through the center. All right, and Y is your stress value in here. X is your strain value in here, and E, it tells you the um, the slope of this line. Let's say you have a rigid material, you have a less ductile material. This line, it will look a little bit tilted, like it's gonna go along here. Can you guys follow my cursor? So it's gonna be a little bit more steeper over here. If you have more ductile material, it's gonna be a little reluctant, so it's gonna go along here. So your E, that's gonna define how steep your curve looks like, and that E is a property of a material, meaning how ductile or how rigid the material is. So it's an intrinsic value of the material, and you can find it like people have been doing a lot of researches to find these values for a lot of different materials. So you can always find the values for these materials for this modulus of elasticity online. And then comes the yield strength. Yield strength, as I mentioned, that after this point, you will have a permanent deformation. So that point is called yield strength. So if you, let's say if you have designed a vessel, so the vessel only has value when you can use it for your application, and after that it will still hold its initial properties. It doesn't degrade its properties. This is when it has values. But once it reaches a yield point, once it gets a permanent deformation, even if it's not broken all the way, even if it looks right, it looks normal, but still this thing has lost its values, and you have to throw it away because it's not safe anymore. So we all, whenever we're designing something as an engineer, we always focus on yield strength, which is a lot before the ultimate or the fracture point. So it gives us a safety range. Then comes the ultimate tensile strength. Already talked about it. The elastic region. The elastic region is where if the stress is released from the material, it will return to its original state. So this area, this little area from the starting point up to this point, the plastic, the elastic region point, and this little triangle. That's what's called the elastic region. And the plastic region is the other thing where there is a permanent deformation. Okay, so now comes strength hardening. Um, so after plastically deformed, dislocation move and additional dislocations are generated. So what's dislocation? If you look into this picture, you will see that all the materials, all the metals or plastics or whatever you say, they have these little gaps in their grains, in their molecules. So when you put it under strain, what happens? These gaps, like since you're putting it under force, you're kind of like pushing it from sides. So these gaps will, they will get filled up. So instead of increasing the area, it's gonna fill up this volume and it's gonna decrease it. But also on a tensile load, what's gonna happen, like you make more gaps as well. So for example, if you pull this grain from both sides, you will see that there are gaps forming in between, and that's how eventually those material are gonna get fractured. For example, let's take a look at this one. Um, what's happening here? We call it necking. So you're pulling it apart. You're pulling it apart, and over here, you're kind of like acting on those grains. You're pulling these molecules uh, like apart from each other, and eventually over here it breaks. So another important phenomena that you need to notice here is over here your cross sectional area is changing. So if you think about this cross sectional area, whatever the force is, it's getting divided by this total area. But in here, that area is much smaller than this one, but that your force is same. What it tells you that in this area you have way higher stress than this area. So if you have a breaking point that has to happen over here, we can reach to another conclusion, is that whenever something breaks, we know that any material is not going to break at all the points. It's going to break at one point. So uh, which point is going to be? It's that's the point where you have the minimum area. This is where you will have the maximum stress, and this is where you will see the failure. So um, so whenever you are designing something, make sure that your critical area, the area with the minimum cross section, will have has a safety range, so that can your critical area can withstand the maximum load. If that can withstand it, then your whole specimen or your whole design can do it as well. All right. Any questions so far? Mm, okay. Uh, so from the next class, what I'm gonna do, I'm gonna pick you guys up. I'm gonna ask you by name to like answer me something, just to make sure that you guys are still in the class. Sergio is asking if the plastic deformation is same as a yield strength. Okay, so yield strength, it's a value. It tells you how much force this specimen can take. And plastic deformation, it's like it's an event. It's not its intrinsic property. You just measure it to see how it deforms, like how much it deformed. Um, so like you're looking at the same thing but from different angles. Did I answer your question? Does it make sense? Okay, Wally's asking what's the minimum safety factor we need to design to get approved. Well, it depends. It depends. Like let's say you have a very crucial or you have a very important uh, um, experiment. For example, let's say you have a rocket You are on the moon. You have no other resources available to you, and it's very crucial. So definitely, you want to have as much safety as you can. But let's say if it's just a rod that you need to use to build a local experimental setup. At that point, you basically don't need to put too much material in it. You don't need to, spend too much resources to make it safe. It can break. It's a one-time thing. So, it all depends on your application. As I told you that your slope of this yield strength linear region length, it's an intrinsic property of material and it changes. This curve says the same thing. So when you have, in general, plastic materials, they kind of looks like that. But when you have soft rubber or like a very ductile material, your slope is much lower than this, and it's gonna look like that. But when you have brittle material, your ductility is very less, so you have a much steeper slope. However, in brittle material, you won't be able to see any plastic deformation because after this point, there won't be any deformation. It's just gonna break. So study these curves and see what material produces what kind of curve, and then you have to compare it in your lab report to say that hey, my specimen falls within this region. All right, now comes the fun part, the experiment. What are we doing here? We're printing a material, a specimen. The specimen kind of looks like that. You have all the dimensions here. We're using over here, it's PLA. It's a plastic material. And if you, like from the video, you have noticed that this little nozzle, it's like a pen. It moves in a direction, right? You're writing something, but uh, you're like on top of each layer, like you're creating layers. So those layers, like you can move this thing along any direction. It can move from this point to here. It can go in z direction, meaning from the front to the back. So our goal here is to check how the direction of this printing affects when put under tensile load. So we will study 3 different angles. That's the first angle, 0 degree. That's the second, 90 degree. That's third, 45 degree. In other words, in 0 degree, your tensile load will have 0 degree with these threads, with these fibers. When it's 90 degree, your tensile load have 90 degree, and when 45, you have 45 degree. Any question? Okay. I will upload the experimental video online. It's quite long, so I'm not gonna like show it here in the class, but you will find it on Blackboard. But just let me tell you how it works. So this is your tensile load setup. You'll put the specimen in here, and you have this button, and there's a little computer screen that gives you values at each single point. So you don't have to manually get those values. So what this thing is doing, it's pushing it from opposite direction. Like this little bar over here, it's going up and up. So it's putting tensile load on this specimen. So eventually, since you're putting tensile load, it's gonna break. It's gonna break somewhere. And where should it break? Of course, where you have your critical area. Like you can predict that it's not gonna break along here or along here. So somewhere in this area, most likely here. But why? You have to explain it in your experiment. So look into it. Like why in a specific position or in a specific area it breaks. Okay, I'll give you a hint. See, like over here, whatever your area is, here you have the same area, similar area. Still, it breaks here, not in the middle. And why is that? Look into it. Okay, so by the way, this setup, it only gives you uh, the the data for the deformation. So you have to calculate by yourself how to find the stress and strain from just a deformation. Hold on, I'm trying to share the data with you guys so you have a better idea. All right. So these data we got it from the computer. It has a lot of data, like it gives you data at each 0.001 time interval. So you can see that how many data it's gonna be. So, but what you have to do, you have to make sense of all these values. It's such a long list of values. How can you do it? You have the load. You can definitely find the areas from there, from the dimension. So you will have your stress, and then you have the positions, right? So your positions change, meaning you are seeing a deformation, you're seeing a strain. So you got to calculate the strain from there as well. So you have your initial length, and then you have your change in length. So you can get your strain and you can get your stress. So plot them in a curve, then explain them, and uh, that's how you write your report. Remember, it's very important that you explain them. Just plotting the curve or just getting or preparing these values is not enough, because the goal of the experiment is for you to understand why these phenomena are happening. All right. Experimental procedure: touch the specimen to the tensile testing apparatus by bottom zig. Bottom zig is this little zig in here. Open the Metscutor, I don't know how to pronounce it, operating program on your computer. So this program comes built in with the whole setup, and it's made in LabVIEW. I don't know if you guys are familiar with it or not, but LabVIEW is kind of like a GUI that where you can control any sensors, any you can any electrical instruments, and you can read values from those sensors as well. Put the desired load rate and deflection rate on the software. You can define those in the software. Obtain the load versus position curve. You already have that. Observe the fracture location. Plot stress strain curve. Repeat the same steps for all specimens. Take pictures. Compare fracture modes. So, you'll see different, you'll see fracture, but they will look different. Perhaps not. But you gotta explain those, what kind of fracture you're looking into. For example, when it's brittle fracture, as I told you, that you will not see any change in cross-sectional area because the ductility it's pretty high for brittle materials. So after one point, it's just gonna break, hush, like that. And for like when you have ductile fracture, definitely you will see a necking because those grains they're changing, they're they're deforming. So you will see a necking, you will see a length change, and eventually it's gonna break. All right. So that's pretty much it for this experiment. Now, so for today's for the next experiment, second experiment, what we're gonna do, we're gonna observe the fracture in specimen. How much energy is absorbed during fracture for different material, the energy lost during fracture, and the importance of fracture toughness as a material properties. These three objectives we're going to study in this experiment. Well, you guys have seen what tensile load is, but what is fracture? Fracture is when you put a lot of force in an area of a specimen, but for a very small time amount. So what's gonna happen here is that this little hammer, it's gonna hit your specimen and it's gonna break it. Now you're gonna study how much energy needed for this hammer to break the specimen, and you're gonna compare different specimens of different materials, and you're gonna calculate how much energy you lost just for the swing without the specimen, meaning uh, what's the resistance of the air or the friction, and how they impact the overall experiment. Let's go through these points. Impact test determines the amount of energy absorbed by a material during fracture. A material's toughness is a factor of its ability to absorb energy during plastic deformation. It pretty makes sense to you guys, because we already talked about tensile. We already watched the stress strain curve. So imagine this whole stress strain curve. This is also happening here, but within a very small time range. So your this thing is just like putting this specimen at its fracture point within milliseconds. Ductile material produce high impact values. Well, it also makes sense because ductile materials can absorb much more energy than brittle materials before breaking. So, ductile materials will need much more impact force than brittle materials. Also acts as a tool to study temperature dependent brittle ductile transition. So the way it works that you have a ductile material, you put it under impact, you see how much energy it absorbs, then you put it under heat. So the ductility goes away, brittleness comes in. And how do you study the brittleness? You do the same test, and you will notice that the force you needed before is much higher than the force you're using now. There are two different types of impact tests that you can do. That's the Charpy test, that's the IZOD test. So Charpy is pretty much a V or U-shaped notch you have over here. Now, why do we have a notch? It's because you're reducing the area in here. You're making sure that this specimen breaks specifically over here. Also, you're creating a notch. Whenever you have a notch is always susceptible to break. Let's say you have a circular area over here, like a circular shape. Even if your area is lower, but it's not going to be as effective as if you have a V or U notch in here, because a notch specimen is usually. So how does it impact this? Like, how can you calculate the amount of force that's being used in here? So you all are familiar with the conservation of energy law, right? And we know that the energy just converts from one form to another, but it doesn't really change its magnitude. So what you do in this experiment, you put this hammer, you put it in a height, and when you put it in a height, you're giving it some potential energy. But this is the energy you're gonna use to break the specimen. So you're gonna let it go. You're gonna let it take a full swing freely. So what's gonna happen? This potential energy, see, as this head, it's changing its height, right? It's changing its height, and at this point, it has a minimum height. But over here, it's gonna all this potential energy, it's converting kinetic energy. So you are gonna see a high velocity in here. And just as it moves this point, again, it's gonna increase its height. So again, those kinetic energy is gonna convert into potential energy. However, initially, however much potential energy you have over here, you have much lower in here. and it's because some of the energy will be absorbed by the specimen. Uh, mm, so you didn't hear me saying the last things, the last slide? Yeah. Um, Still having issues or not? Because I just changed my microphone setup. Okay, maybe it's my microphone then. Let me. You guys can hear me now, I know, but it's not gonna be as clear as when I had the microphone. I mean the speaker on. But is it comprehensible? Okay, okay, all right. Wait, so were you guys having the same issue like throughout the whole class or just this time? I hope it's not the whole class, guys. I talked a lot. Okay, all right, yeah. Okay, so well, let me start the slide again. So you have this little hammer over here, and this hammer is gonna break this specimen. But how is this gonna happen? You have to put some energy, you have to put some power into the hammer. And how you can do it? You can put it in a height. For example, you can put it in a height h1 from your surface, and it's gonna put some potential energy in it. And I'm pretty sure that you guys are familiar with the law of energy conversion, meaning no energy can be created or destroyed. It just converts from one form to another. So this potential energy, when you let it go, as it decreases its height, this potential energy is gonna convert into kinetic energy. And eventually with that kinetic energy, this thing is gonna heat the specimen. So let's take a look at this picture. You have this mass hammer in here. It's changing its length. You let it go full swing. It's changing its height. It's changing its potential energy. It breaks the specimen, and as it moves away from this point, it gains height. So at this point, it has maximum kinetic energy and minimum potential energy. At this point, it has maximum potential energy and zero kinetic energy. But as it moves away from this point, it's again gonna go up, but it's not gonna go up as much as it was before. Like H1 and H2 is not gonna be similar. H2 is gonna be much smaller than H1. So you have a change in your energy, and that change is what's absorbed by the specimen. This is how much force, impact force, your specimen can take. Any question? All right. Okay, so what's the equation of the potential energy? It's mgh. So you got your first h1, which is the length of this hand r, and then you have r sine alpha minus 90. How are you getting this alpha minus 90 thing? Well, that's the angle alpha, right? This is the angle between your central axis and this little angle over here. Well, I think I got a couple of questions. Okay, Arturo is asking if there are any friction in the system. I'll explain that in a bit. Um, yes, we do, but let me finish this slide first. So you have this R, this length, but you need this length. How you can get it? Um, if you let it swing, if you let it rest in this here, you'll see that this height, the first like the height that R, that's always gonna be here. This little height H1, it has the component R in it, so you have the R. However, you still move it a little bit upward, so you still need to find this little length from like this line up to this point. How you can get it? You can use the vector division formula. So if you know the length, if you know the angle, this angle of this triangle, you can use the sine of this angle, and you can get this height. And how you can get this angle? You have to calculate this angle from the starting position or from the zero position up to here. And your experimental setup, that's going to give you this angle, this alpha angle. So all you have to do is just plug in these values in here, and you can get the H1. Now it has a negative 90 with alpha because you're just concerned about this little angle. You don't care about angle from here to here, and that's 90 degree. So you subtract 90 from the total alpha value. Similar thing happens on the other side. It goes over here, and then your experimental setup, it gives you the value beta, and you calculate this H2. You subtract H1 from H2, and you'll know how much energy your specimen took. You plug the value in here, mg H1 negative H2. And M is definitely the M of this hammer, not this specimen. Just make sure. You plug all this stuff in here. This is your final equation. You will get the alpha and beta value from the experiment. You plug them in here. You will get the energy absorbed by the fracture. Any question? All right. Okay, so that's a little bit more explanation on ISO test, like how to grip it, where the struck blows, and how the energy absorbed is measured. I already talked about it, and also video talks about it, but let me know if you have any question on the detail theory. That's how the experimental setup looks like. So I don't know if you can see it, but this little hammer over here, let's see if I have a better picture. No, okay. So this little hammer over here, that's the value, that's a hammer, that's a M, that's a mass that you're looking for. So you take this, you put it here along this little hand. So you're putting it in a height, so you're giving it some potential energy. You have a button, this little black button over here, this one. You press it and you let it like swing free. It breaks it, it goes over here. You stop the experiment, and the value of alpha and beta will be shown in this screen over here. I will upload the experimental video so you can have a better visual access, but I think for now it explains. Any question on the experimental setup? All right. So you'll use 3 different metal specimens. You will have a brass, aluminum, steel. So you'll compare these values that you get for all these 3 metals, and you figure out which one is more ductile, which one is less ductile, and all. You have to explain it in your report section, in your discussion section. All right. So it's just the procedure that I just explained. First, took this hammer, uh, put it in a height, let it go. It's gonna break, and then make sure that the specimen is in the right position, like meaning that um, see that specimen it has a notch in here. So you want to make sure that your hammer it hits exact on the opposite side of the notch. So in that way, you will have a symmetric value. If it hits somewhere else, then you have to do some additional calculation to make sure exactly how much force this notch is seeing. So you can you have to do an extra stress analysis but we don't want that. All right. Okay. So now to answer the question, do we have friction in here? Yes, we do. See, this hammer, it swings through this bearing. So it's a metal surface contact. So definitely there is friction. That's a big loss. So whatever energy loss you will see using this equation, not everything is absorbed by this specimen. Some of them will be lost by the metal friction. Some of them will be lost by the air friction. Because even though you see this thing, it has a little glass window in front, so we're trying to make it as less separated from the environment as possible, so air doesn't include much of the experiment, but still, it doesn't help much. So there are some loss due to the air friction. So you have to calculate those as well, and then you have to subtract these values from your total loss. Only then you can find the values of the impact. But how you can find those losses? What to do? It's pretty smart if you think about it. You just take the specimen out from the setup and you let this thing swing free. So when the specimen is not there, this air friction and the metal friction are still there. So you will still see a little bit of change in the height, a little bit of loss. This is what your loss in the experiment. So after you let it swing free, you get those values, you plug them back in here, and you will find the impact force for the specimen. Question. Why does a specimen have a notch? Well, I already mentioned it a little bit, but okay, let me go over there. So remember we talked about the critical area where you have the minimum area. This is where you're going to see the breaking. So we want to know the parameters that we are controlling. So we want to know how much area we have over here. That's why we make this notch. So we reduce the section, area section, and also when you have a notch, when you have a V notch, you have a stress concentration specifically in this area over here. And that is why, I don't know if you guys notice it or not, but when you buy those chips, those plastic chips packet, they have this notch on top of it, like a ray of notch. This is where you tear the chip chip bag apart, right? So imagine if you had a straight top, it would be much harder for you to tear the packet apart. But since it's notch, you just pull it and it comes apart. So that's the whole purpose of the notch. It makes sure that your specimen breaks at specific this point. So you're reducing the area and you're increasing the stress concentration. Does that answer your question? All right. So yeah, I mean, at this point, you pretty much know what goes in your resultant discussion. The average energy absorbed for each material, meaning you have 3 different materials and you run the same test for each material 3 times. So get the average value, find the air resistance, subtract them, and make a comparison. These are your values. I'll also upload them on Blackboard. You have your alpha degrees here. The betas are not here, but um, I'll let you have access to it. And finally, you analyze, you compare different modes of failure. The similar thing that you did in tensile load, but that's different than tensile. So you have to make a comparison. How is it different? Why is it different? Arturo, you're very late in the game. Arturo is asking, how do we account for the air resistance? Well, I think if you go, like I already explained it, so if you go through the video, I think it's gonna answer your question. But yeah, like I'll upload the lecture, and if you go through the video lecture, it'll answer your question. But let me know if you still don't understand it. All right, so that about it for the two experiments. Now, what's your feedback? What do you think? Any question? Any confusions? Anything needs more explanation? All right. Well, we will be uploading this slideshow to Blackboard. No, I'll put the video on Blackboard or YouTube. Yeah, I'll send you guys a link. So yeah, don't worry about it. Anything else? All right. If not so,